Okay, so what I'll do is a rundown, because 4a is finite difference, which is so similar to the other ones. So I'm not really going to comment on that. So I guess it's a way of seeing how well you retain stuff from the previous finite difference problems, because you're doing some similar tasks, like setting up a matrix, doing an error analysis with Taylor expansion, and all that good stuff. For B, on the other hand, so we have an actual spectral method, a Chebyshev spectral method. So with this being your PDE, on the interval -1 to 1, which is the natural interval to use for Chebyshev, and then 0 on the boundary. Okay. So, like finite difference, you're going to take this PDE and get a linear system from it. We're still going to have a u is equal to f system, where the vector f is just going to be all ones. Okay. And what about the matrix A? So matrix A is going to be minus epsilon dn tilde squared plus dn tilde. So now I need to explain what these dn tilde matrices are. Okay. And dn is given in the notes. Okay. Now, dn with no tilde first, I'd have to define is in the notes that are posted on the site, page 20. Yes. It's like you're a designated person to dig stuff out of the notes. Okay. Now, in the notes, this is called D. I put the subscript N to indicate it's for N grid points. So then, dn tilde is dn with the first and last rows and columns deleted. Okay. The reason for that is the x values for a Chebyshev method include the endpoints. So they include x equals -1, x equals 1. But those are not unknowns in this case. We know the solution is 0 at those points. So we don't need to, so we can delete the rows because we don't need those equations in our system. And we delete the columns because we don't have those unknowns. We don't need those unknowns in our system either. So that's why the first and last columns are stripped out. Now, the matrix is, I'll check my notation here.
So the first and last rows and the first and last columns?
Yes. Yeah, so 2 rows, 2 columns gone. So now dn, no tilde, is n plus 1 by n plus 1. The dn tilde is n minus 1 by n minus 1 for however many grid points you have. Okay. Now, as for dn tilde squared, I'll be very careful about how this is defined in terms of what order things are done. Really what you do is you take dn, the original dn, square that because then that's the second derivative operator, because the dn by itself is first derivative. And then, it's like I'm doing the tilde last. In other words, you remove first and last rows and columns from dn squared. Very important that you square, then cut. If you cut the rows and columns and then square that is a matrix of the same size, but it'll be wrong.
Is the easiest way to do this would be to build dn
Mhm.
like
Yeah.
normal, and then do like is it the same way we would have done whenever you make the whole column 7, or was the last entry 7?
Oh,
Like you just build the matrix
Yeah.
first and then just modify it.
yeah. Really, that's the only way to do it.
How do you delete the column?
Well, okay. So, I need to talk about that. So squaring is no problem. Just square it normally. So, I'll talk about row removal. So, if I want to strip out the first and last rows of D, then that means I'm keeping rows starting from row 2 all the way to the second to last. So end refers to the last row available, so we're going to deduct 1 from that. And here in this case, I'm only removing rows, so I'm keeping all the columns. But you get the idea as to how to do the same thing with columns. And it can be done in one shot. So really, you're not really deleting, you're keeping the rest. You're specifying what stays. And so since really I have 2 classes this semester that deal with MATLAB, this one and 460, 560, the thing I notice students having a lot of difficulty with is just how to index properly. When you're using, in MATLAB, indices are always enclosed in parentheses. When it's a single index, like A parentheses K, for instance, that is an element of a vector. So A of K by itself, that refers to a number that's one element of a vector. Always use 2 indices when you're extracting part of a matrix or setting part of a matrix equal to something, where you're specifying rows and columns. It might be an individual row or a set of rows, like I have here, but still you're specifying row, comma, column. I see a lot of cases of people saying like A parentheses K equals to something that's a vector. Well, you can't, because A of K refers to a number. I can do something like this. D colon comma 1 refers to the first column. So that would be a vector. I can set it equal to another vector. So it's always important to keep in mind, as you use indices, what kind of object do you want to be working with? What kind of object are you actually working with for a certain kind of index?
For dn, where there's dots on the left and right, is it saying that first entry just goes on forever to the left and the last entry goes on forever to the right, but the middle is...
Okay, so you're looking at the big old monstrosity in the notes? Yeah, that's the next thing I want to talk about. Okay. Yeah, because this matrix set's kind of weird. It's a bit more complicated than finite difference, where you just have a...
Or is it not this one? I mean, it doesn't look that bad. No?
Oh, no, not that one.
It's like
Okay, that's the other one.
Yeah, you're talking about the periodic one. You need to go to a...
So do the DIJ one.
So there's a setup below that has it blocked off into 9 areas.
Okay.
Mm-hmm.
Yeah, because that one you described, we could use SP diags for
Yeah.
that. Yeah.
So this one you would have, I can't even wrap my head around how to start it, but
Okay, that's why I want to talk about it. Yeah, because I figured when you saw that, it's like, okay, what is this? So, okay, make sure I can get all of this. Okay, so dn equals. All right, so really there's 9 cases. Well, actually, really more like 10. Okay, so as far as how you refer to these, it would be best because you're going to have your x values are indexed from 0 to n. This is an n plus 1 by n plus 1 matrix. So you're going to have a vector of x's, and the x values are defined on the previous page. It's at the bottom of page 24. You have a formula for your x values. So we're going to assume so xj plus 1 would be equal to cosine pi j over n. And j goes from 0 to n. Now, here's what's inconvenient about MATLAB indexing. That MATLAB indices have to start at 1. So that's why I have a j plus 1 here. So going into this matrix setup, you have that vector because you're going to refer to it in making this matrix. So what I would suggest is you're going to have a loop, 2 loops, I and j going from like 0 to n, or 1 to n plus 1, if you prefer. You can really do it either way, as long as things work out consistently. And then what I would suggest is, for each of these cases, have an if statement that covers all of them. Like for instance, if you're in the first row, you're doing these 3. So within that, if you're in the first row, first column, you do this. First row, last column, you do this. First row, otherwise, you do that. So how you can set it up is if you're in the first row. So in other words, I equals 1. If you're counting from 1 to n plus 1. Then, inside that, if you're in the first column, that's this case. Else, if last column, do that. Else. So that's row 1, columns 2 to n. So in other words, that's that case. You end that. So in other words, now the first row is completely covered. Else, if last row, same thing, same kind of if statement like this to handle first column, last column, everything else. Else, again, you're in the middle here. You'll have another like this. First column, last column, everything in between. 9 god-awful scenarios. What's more, after you've handled that, and that, those 7, 8,
yeah, isn't the middle one actually have 3 scenarios?
you can do it in 2. So in here, there's one formula for the main diagonal. So in other words, I equals j. So you can check for that and handle the diagonal. And then,
I equals j is back.
yeah. And notice For the off diagonal, the same formula is used.
Yeah.
So that's your else of your else of your else, pretty much. Yeah. Okay. Um, now, once you've identified which case you're looking at, the actual formulas aren't so bad because you're just dealing with -1 to some power, or you're referring to your x values. And then the corner entries don't even do that. So um, you just have to be careful with the indexing. That in the formulas given in the notes, there's all these references to xi, xj, and so forth, and those are going from indices are from 0 to n, but that would correspond to elements of this x vector 1 to n plus 1. So you just have to be mindful of that. Okay. Yeah, there are these formulas that are right above that for Dij. One for the diagonal, one for the off diagonal. Each one of those is pretty dang tedious. So I'm not sure which is the more unpleasant, to be honest. But you could go either way with that. Yeah, so for example, in here, you'd have 2 times -1. Like, okay. -1 to the j over 1 minus x j plus 1 if, and this is very important, if you have j go from 0 to n, because then that is consistent with the formulas given in the notes. Whereas if you decide you'd rather have j go from 1 to n plus 1, you could have j as the index, but then you have to have j minus 1 up here. So be consistent, and it'll be okay. But yeah, if MATLAB had zero-based indexing, it'd be a whole lot easier to translate formulas and algorithms from books into MATLAB. Okay, so any questions about this very tedious setup? Okay. So once you do this, and you're able to set up your system and solve. Then what will happen to both parts A and B is that for smaller values of n, the solution is pretty terrible. They exhibit oscillations. As you increase n in both finite difference and spectral, the oscillations do go away. Just that solution so badly behaved because it goes up and then comes back down very sharply. So that's a function basically has a discontinuity in it. Is difficult to represent accurately with numerically because of that sharp discontinuity. But if you have enough grid points, then it looks okay. So, but the idea is this problem illustrates that for a problem like this, with Chebyshev polynomials, you don't need quite as many grid points to get an accurate solution as you do with finite difference.
When you do the for loops, doing a for loop for the rows first.
Um,
Then you're doing
right. Yeah. So rows and then columns nested within it. Yeah. So
but you said there should be 2 for loops.
yeah. One nested within the other.
So just say them right after. the
Yeah.
other.
Yeah.
And they're the same size.
Yeah. Because it's a square matrix. Okay.
Are you gonna do hints on 5 now, or are you gonna wait and do those later?
What would you prefer? I can really go either way with that. But
I mean, I guess go ahead and just do it if you're recording it. We have it.
yeah. Because also we don't meet for nearly 2 weeks. So okay. All right. So I will preemptively discuss 5. Okay. And then after that, there will only be one other problem. Multi-grid, and I'll save that for maybe I'll come back. Okay. All right. So number 5 is periodic boundary condition. It's the same PDE, except now we're on the interval 0 to 2 pi, and U is 2 pi periodic. Periodic. Okay. Okay. Now, part A is on paper. You're showing that there's a condition that F has to satisfy for a solution to even exist. And there's really nothing to say about that because I actually covered the exact same thing in 2 dimensions. So the answer really is the same thing described appropriately for 1 dimension. So I'm just going to refer you to that. I'm going to talk more about I'm sure you guys have ever had me spend time on talking about the coding part anyway. Okay. Part B is, again, finite difference with a slight change from what you've had before. Okay. Now, so what your matrix is going to look like is the same matrix you're used to for minus Laplacian, where we have 2's in the diagonal, minus 1's above, minus 1 below, blah, blah, blah. But then, because of the periodic boundary conditions, there's a wraparound effect. So here, we have minus 1 times a point to the left of this, but by periodicity, that would be the last point. So minus 1 goes up here in the corner. And again, down here, for the last equation. So this is a circulant matrix that comes up all the time with periodic boundary conditions. Okay, and H is going to be this difference 2 pi over n, whereas before Dirichlet boundary conditions, it's the interval length over n plus 1. Because here we're actually including one of the boundary points in our grid. Okay. All right. Now, one thing that's going to be a pain about solving this system, because you can solve AU equals F like always, but there's one problem. A is singular. In other words, it's not an invertible matrix. Now, you can go ahead and feed it to backslash anyway. But what will happen in that case is there's one or two possibilities. Because in part A, it says you find a condition on F so that there is a solution. If F does not satisfy that condition, there won't be a solution at all. Whereas if you use an F, now did I specify an F? Okay. In part D of this problem, there's two actual F's given. Okay, so you use it with that. So if F does satisfy the condition for part A for a solution to exist, the solution will not be unique. So what you need to do after, so go ahead and solve AU equals F like usual using backslash. And so even though the matrix is singular, backslash will produce a solution anyway. It just may not be the solution that you want. You want the solution that has a zero mean. So, so in other words, you're going to remove the mean from U, and fortunately, I do not have to tell you how to do that because it's already given in the hints file, like the actual MATLAB code to do it. What you're doing is you're actually orthogonalizing U against the constant function. So you're stripping that part out, which removes the mean. Okay. So that way you can be sure you're getting the solution that's expected. Okay. Now, part C, same idea, but now it's using a spectral method. So the matrix involved is defined on page 24. Well, there's two matrices there. There's the dang it. Okay. Sorry, I was just having an iPhone delivered to my uncle in Cincinnati, and the name on the door said Lambert, because that's where my dad used to live. But his name is Eigelhart, so the phone guy was like, nope. So. Yeah, I just send phones to random addresses for fun. Yeah, sure. People. Okay, and have I gotten any email from AT&T about it? No. Okay, so, all right, so matrix is given on page 24. Well, there's two matrices. There's one for first derivative and one for second derivative. So both of these matrices are toplets, meaning they have the same entry down each diagonal. So you can define using either diag or SP diags to fill in all the diagonals. So it's like this situation where here you have the same element down each diagonal. The difference is in the spectral code, every diagonal, except possibly the main diagonal, is non-zero. So it seems kind of weird to suggest using SP diags, because SP diags is for a sparse matrix. This matrix is not going to be sparse. Practically the whole matrix will be non-zero. So you might just want to use diag in that case. Yeah, you're going to be filling in a two-dimensional array anyway. So on that page, there's a first derivative matrix. So you could fill that in and then square it. Or there's also the second derivative matrix, but you can fill that in instead. So you have to look at the patterns, like what are the entries that go in each diagonal, and then fill those in. Although, what might work just as well. Okay. On page 23, entries of the first derivative matrix. It's kind of implied by one of the formulas for u prime of xj. So what I'll do is I'll write down the formula for that entry. So djm is equal to minus 1 to the j minus m times cotangent of j minus m h over 2, cotangent of that whole thing, where, okay, j and m go from 1 to n. So this is an n by n matrix, and h is again 2 pi over n. So what you could do is just have a nested for loop that just fills in that matrix. What this leaves out is that the djj diagonal entries are 0. You would not get that from this formula. It would give you like infinity or something, because cotangent is undefined at 0. So diagonal entries are 0. Off diagonal entries are this. So you can just fill those in using a loop that goes like j for j equals 1 to n, for m equals 1 to n. Fill that in. That's your first derivative matrix, and then square. It'd probably be easier than using diag or SP diags or whatever. Okay. Okay. Part D is where you're given specific functions for f of x. And the idea is you go ahead and solve a problem for different values of n, look at the error, see what the order of convergence is. It says run error analysis for both codes, so finite difference and spectral, to see how they compare. Like, do you see second order accuracy, which is what you'd expect for finite difference? Do you see something greater accuracy than that in the spectral case, or is it the same? So it says run an error analysis, I'm not talking Taylor expansion. There is no Taylor expansion in this problem. It's all just what you see in MATLAB from the errors. For two functions, the first one, because you have to find the exact solution, like you've done in other problems. Now, for the first one, the f of x is just a sum of some signs. So that's easy to integrate twice. The other one, you're going to hate me for this one. It's a piecewise function, which, yeah. Okay. Yeah, your face says it all, or all your faces. um, well, okay, it gets worse. Um, yeah, it's a function defined in two pieces. Oh wait, no, three pieces. Because it's equal to -1, then jumps up to 1, and then back down to -1. So like the end of problem 2, you integrate it twice, and you have your plus c's, and you have to make sure that the function and its first derivative are continuous. Um, hmm. You know what? This problem is pretty sadistic. Okay. Um, okay, I actually feel kind of bad giving this one to you. So I'm going to make a deal with you. so in part D, like I said, there's two F's. I will require you to do the first one, because that's not going to be hard anyway. That'll give a good comparison of finite difference versus spectral. After that, your choice is to either do the other one or problem 6, the multi-grid one. So I'll let you pick which one of those you want to do. Yeah, because when I
Or 6.
5 double I, D I.
yeah 5 yeah so 5D double I or number 6.
If you had to choose which one to do, which would you choose?
Okay.
That hesitation is not nice.
Yeah. Well, my reasoning might not necessarily be the same reasoning that you would use, but
Okay, well, answer in respect to if you were us.
okay. Actually, I'm not sure if I would change my answer. Well, here's my reasoning. I would choose number 6. Now, I guess the more professory kind of reasoning is, well, that problem's more interesting because trying to do because in problem 5, based on part 5DI, you're already doing an error analysis. The actual skills related to finite difference versus spectral already done. This is a monstrous, integration exercise and solving versus constant integration and so forth, and having done it before, setting up systems of equations, and what I mentioned is, like, okay, when you had to do the same kind of thing in problem 2 at the very end, you had like 4 plus c's, and that's a system you went ahead and solved on paper. There's no solving this one on paper. It's 7 equations and 6 unknowns. And what I say is, okay, you can figure out what the equation should be, but you might as well have MATLAB solve them. That's actually an overdetermined system, but whatever. Also, can you imagine, and I did see this happen with students working out this problem last time, that you go through all the trouble to set up a system and then you find out it's wrong. And you have to go back and see what you did. Problem 6 is not easy either, but I'm hoping at knowing where the difficulty comes from, for as far as you guys wrapping your heads around recursion, which threw off people last time, but now I'm ready for that. And that's why I talked about it so much last time. I I think that will go more smoothly than it did. So, so I'd recommend problem 6. But if you feel that the whole idea of multi-grid is just like, then I won't begrudge that, and you go ahead and integrate your head off. So, yeah. So it really is a pick your poison kind of thing. But I figured I'd have you ingest 1 poison instead of 2 because I don't want you to hate me. So. Okay. All right, and so problem 6 is something I'll talk about when we come back from stuffing ourselves with turkey, etc., and canned cranberry sauce. Okay. What?
I don't think we're having turkey this year.
Oh, really? Oh, okay.
I'm confused.
Everybody has their traditions.
We do ham and turkey.
You do what?
Steaks this year. We're like, we don't want turkey.
Oh.
It's not important.
Well, I can relate because for a while there, if we weren't visiting anybody, especially since living here in Mississippi, sometimes we get invited to someone for Thanksgiving, but if not, then it's just
I mean, why? You don't have to have turkey. I mean,
Yeah.
If I could choose between turkey and steak, like I would totally choose steak.
Yeah.
So why
Yeah.
not just have steak?
yeah, and because the thing is, then Di and I would just have our own Thanksgiving, but she's a vegetarian, so I get all the turkey. So of course it'd be a small turkey, and it still have a zillion sandwiches off.
Turkeys are expensive. I mean, you
Yeah.
can spend money on some.
I would like to do the turkey if you like do the real stuffing, where you stuff.
Yes.
Yeah.
Like, rather than that, just a dry turkey.
But yeah, but we're a couple years, like 2015, 2016 or so, where I actually did have steak on Thanksgiving. Like we would like go to New Orleans or
We're gonna have turkey and ham on Christmas anyway.
yeah. And since there were certain restaurants that be open on Thanksgiving, it's like, so I can't fault you one bit. So no.
This these adult statements are just
Mm.
I don't know. How do I do with the actual building the matrix part? Like whenever I do the actual statement and the adult statement, because what I'm doing right now is I have a card where I keep pretty much every because I have 10 like I picked a block. And I'm going to assign it to that letter and then I'll just build the matrix with that letter.
I'm not sure where the actual letters are coming into play though, because your indices will still be based on I and J.
Yeah, see all what I'm doing.
Okay, then I guess it's something I'll have to look at. Well, I'll give you an example.
Like what would you make your statement in this case?
Like this one right here.
Yeah.
Yeah, so what I would say is, so my matrix, D, row 1, columns 2 to n minus 1 is equal to, and I would use this formula, but in a vectorized form.
Wait. Where is that going though? Because is this inside the if statement?
Yeah, so this statement would go right there,
Under that?
in place of this. Yeah,
So
row.
you're not saying I equals 1.
Oh yeah, for these conditions, yeah, I'm saying if I equals 1, then I'm here. If j equals 1 also, then I have this case. If j equals n plus 1, then I'm in here.
Okay.
Otherwise, so here I'm filling in the first row, everything except the first and last columns. And
So okay.
so actually, and even though this is a formula for one entry at a time, here's how I can do it in one shot. I can do 2 times minus 1 dot exponentiate. Now, wait. J equals, sorry, these indices are wrong because I should not include the first and last. It's really 1 to n minus 1.
2 to n minus 1.
Well, the formula in the notes.
Oh, you're doing from 0.
Yeah.
Okay.
Okay. So what I would do here is, I want to raise minus 1 to these exponents, 1 to n minus 1. So if I do dot exponentiate, it'll do that. This will give me a vector of minus 1 raised to all those powers. And then,
So you can't do just to the power of j.
well, you can,
We had to
if-
follow.
yes, if you do these in a loop within these loops.
Can you just call
I will momentarily. Okay. All right. So do this dot divide, and then I have this denominator. 1 minus x elements 2 to same indices as here, 2 to n minus 1. And that gives me those entries as a vector. And so that takes care of that portion of the first row all in one shot. That's not so feasible for this interior part. That's probably best done in a loop. Or actually nested loops, but yeah, these fringe cases you could do in one statement each if you want to like vectorize everything. Or you can do a loop, as Sarah said. Okay, so before I check out your code, does anyone else have any questions?
Again, when you change that to 1 to n minus 1,
Yeah,
that's because you're doing
because I'm leaving out the first and last rows, or first and last columns.
oh yeah.
Yeah, because those are handled by other cases. I'll try to tell them it's in the class time anyway, and it's nice and dark out. Woo. Okay. Any other? Okay. I'll stop the video and handle any questions that anybody has.